right, quick review. Sampling distributions of sample proportions. So this comes from when we are thinking about taking a sample of a certain size n, and we compute a proportion from that sample, and we do that over and over again for all samples of the same size. And if we continue to do that, there's a couple things we know about the sampling distribution of p hat. Number one, it will be approximately normal if what's called the large counts condition is satisfied. Remember what the large counts condition is? That's that n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. Number two, it will center over the true population proportion, meaning its mean will be p, the true population proportion. Number two or three, as long as the 10% condition is satisfied, we can compute the standard deviation using this formula, the square root of p times 1 minus p over n. Okay. What I now want to talk about today is the sampling distribution of the difference in sample proportions. So let's start by looking at an example with two populations having a known proportion of success. So at school one, let's say 70% of students did their homework last night, and at school two, 50% of students did their homework last night. And suppose the counselor at school one takes a simple random sample of 100 students and records the sample proportion that did their homework, and school's two counselor takes a simple random sample of 200 students and records the sample proportion of students that did their homework. Now, because it's a sample, at school one, we're not necessarily going to get exactly 70% of those 100 students. There's maybe going to be some variability. It could be above or below that. Same at school two. Not necessarily going to be exactly 50% of those 200 students. So if we were to do that over and over again, here's what we know. So at school one, let's say we took a sample of 100 students over and over again, and we computed the proportion of students who did their homework. Here's an approximate sampling distribution of p hat 1. It's going to center over the true population proportion, 0.7. And then we can compute the standard deviation using that standard deviation formula. It's about 0.0458. At school two, we take over and over again a sample of size 200. School one was 100, school two is 200. We know from knowing about sampling distributions of p hat that it will center over the true population proportion 0.5, and we can compute its standard deviation again using the formula for standard deviation, and it comes out to 0.0354. Now, if we look at the sampling distribution of differences, so p1 hat minus p2 hat, here's what it looks like. The shape is approximately normal. It centers over 0.2, which notice that that's just the difference in the true population proportions. That's just 0.7 minus 0.5. And the standard deviation ends up being 0.058. So what we notice, both individual sampling distributions were approximately normal. The difference in sampling distributions, approximately normal. The mean seems to just be the difference in population proportions, 0.7 minus 0.5. And the spread, we'll talk about that. But here is your formulas. All right, shape. When N1 P1 and N1 1 minus P1 and N2 P2 and N2 1 minus P2 are at least 10, the distribution of P1 hat minus P2 hat will be approximately normal. So you're just doing large counts for both samples. The mean of the sampling distribution is just P1 minus P2. And the standard deviation will be given by this formula. These two you don't have to memorize. They are in the formula packet. The shape, the large counts condition, you do have to know. All right, I'll pause it here. Give me a hand emoji when you're good. All right. So just to show you, in the formula packet, right below the one I was just referencing for two populations, you're given the formulas that I just discussed right here. All right, so there's just a visual. This is the sampling distribution of P1 hat minus P2 hat. So again, this is just if we over and over again took a sample from one population, a sample from the other population, computed their proportions of interest, and subtracted them, did that many, many times, this is what would happen. As long as the large counts condition was satisfied, it would be approximately normal. The mean would center over the true difference in proportions, and this would be the formula for standard deviation. All right, so we're going to do one example of this, and then I'm going to give you another multiple choice question from the AP exam to look at. All right, Nathan and Kyle both work for the Department of Motor Vehicles, but they live in different states. In Nathan's state, 80% of the registered cars are made by American manufacturers. In Kyle's state, only 60% of the registered cars are made by American manufacturers. Nathan selects a simple random sample of 100 cars in his state, and Kyle selects a random sample of 70 cars in his state. Let P hat N minus P hat K be the difference in sample proportions of cars made by American manufacturers. What is the shape of the sampling distribution of P hat N minus P hat K and why? So for shape, we always go to what's called the large counts condition. And remember, that's just N times P is greater than or equal to 10, and N times 1 minus P has to be greater than or equal to 10. But we have to do that now for both samples. All right, so let's start with Nathan. He has a sample of 100 cars. His proportion is 0.8. So I'm going to do 100 times 0.8 equals 80, which is greater than 10. And then I'll do 100 times 0.2, which is 1 minus 0.8, which is 20, which is also greater than 10. So check, check. And then let's do Kyle. So his proportion is 0.6, and his sample size is 70. So I'll do 70 times 0.6 is 42, which is greater than 10. Check. And then I'll have to do 70 times 1 minus 0.6, which is 0.4, which is 28, which is also greater than 10. And so the answer to our question is that the shape is normal, since large counts is satisfied for both samples. All right. Find the mean of the sampling distribution. So once again, we're dealing with a difference in two samples, so we're just going to be looking at this formula. Mu of P1 hat minus P2 hat equals P1 minus P2. So in our case, I'll just say that mean mu of P n hat minus pk hat would just be Pn minus pk. So the proportion for Nathan's state we said was 80%, so that's 0.8 minus the proportion for Kyle's state is 60%, so that's 0.6. So the mean of the difference in sample proportions will just be 0.8 minus 0.6 or 0.2. All right, and last, find the standard deviation of the sampling distribution. So again, I'm just going to reference my formula sheet. So we're going to be using this formula, but I'm going to replace P1 with Pn and P2 with Pk. So sorry, I'm going to keep it on here for a second so I can just write this down. Okay. So there we go. Standard deviation of the difference of the sampling distribution of the difference in sample proportions, again, word salad, is going to be given by this formula. So it's going to be sigma Nathan's true proportion, which was 0.8 times 1 minus that, so 0.2, over Nathan's sample size, which is 100, plus Kyle's true proportion, 0.6, times 1 minus that, so 0.4 over Kyle's sample size, which was 70. All right, and that just needs to go into our calculator. All right, got to be a little bit careful with this. I'm going to put Nathan's part and Kyle's part in separate sets of parentheses under the square root. So I'm going to have 0.8 times 0.2 divided by 100, close parentheses, plus open parentheses, 0.6 times 0.4 divided by 70. There we go. All right, so 0.071. And there we go. So if I were to sketch this out, here's what it would look like. The sampling distribution of the difference in sample proportions, p hat n minus p hat k, would center over 0.2. Standard deviation would be approximately 0.071, and the shape would be approximately normal. So now if we were asked any questions about probabilities, about the difference in sample proportions, we could answer that using normal CDF, right? Because we know that it's normal, we know the mean, and we know the standard deviation.